I am super excited to be up here talking, especially wearing this microphone. This is the first chance I've got to do this, and like, guys, you just have no idea. I'm a developer. I'm kind of boring. You can tell because if you look at my laptop, I don't have any stickers on it. I know, right? I've been doing development for about 8 years, and it's been mostly in .NET. Recently, I've gotten into Go, and I really, really like it. I want to tell you a little bit about me as a way of introducing myself. I'm really fond of the letter T, probably because my name starts with it, Tyson. But I also think that it represents something really, really important. You may or may not have heard of this. I'm a believer in the T-shaped software engineer. This is one way to think about it, but I kind of prefer this, where your skills are your breadth of knowledge, things that you know, and then your passion goes deep. And the reason why I talk about this is because I think it relates very much to what I'm going to talk about today. I have a lot of knowledge that I've gathered up, especially about my company and the operations. So that feeds into what I do, but my passion is development, and we've developed our own way of deploying, and that's what I specialize in, and so that's where most of my talk will be about and what I will be most knowledgeable on. I work for Huddle. We're a company out of Lincoln, Nebraska. It's tough for me to sum up really succinctly what we do. We are the intersection of sports and software. Coaches use us to upload their video, to watch it online, to break it down and analyze it, to share it back out with their players. Players use it to highlight themselves and tout themselves, and then recruiters use it to get information on those athletes and recruit them. Huddle.com is our product, and that's where all of our product team spends its time. So I've broken this talk into 3 parts. Part 3 will be pretty short. Part 1 is going to be about the monolith. That's going to be the history of where we've come from. And then I'm going to move into part 2, the multiverse, and that's where things get more interesting and how we actually deploy a lot faster. And then part 3, I want to talk about the lessons that we learned, so basically how you can do it better than we can. So here in part 1, I want to give you the story of how we started deploying at Huddle and kind of bring us up, give you that context that you'll need to enjoy part 2. So I'm going to take you back to 2006. This was Huddle. I'm not in there. These are the 3 founders. They were a mix of business and development. We started with a product that wasn't even called Huddle. We were Agile Sports Technologies, and we marketed exclusively to the University of Nebraska at Lincoln, the athletics department. So we had one customer. We had these dreams that our customers were going to be the Division 1A and NFL teams. The thing is it didn't take us long to realize that it's actually really difficult to sell to those teams, and with only 30-some NFL teams and 100-some NFL or Division 1A teams, we weren't going to make very far. Plus, we started talking to a lot of high school coaches that just kept asking, how do we get this software? And we said, you're not going to be able to get it. That was impetus to go ahead and create a product that was meant for them, and that's when Huddle was born. It was born in 2008. The company was still very small at the time, and coaches felt very free to call us at all hours, especially in the middle of the night. We needed to move quickly to beat our competition. We had some competition already in the space. Nobody was doing what we were doing. We were putting video online for coaches specifically, so I'm not like saying YouTube wasn't around or anything, but everyone who was in this space was doing things on a computer that would then get handed around physically. We knew we could do better than that. We had our share of bugs. Like I said, coaches felt free to call us in the middle of the night. And so what are you going to do when a coach, particularly somebody at University of Nebraska, calls you and says, hey, I can't get my work done? Well, you're going to fix it, and then you've got to be able to deploy it. The thing is that the developers didn't want to spend all their time copying files to servers, and they especially didn't want to do that in the middle of the night. So we had to come up with some deployment software. And so version 1 of our deployment was born. I'm going to introduce you to Alyx, Overwatch, and Outpost. And these names, for those of you who are familiar, were taken from the Half-Life 2 games. I hope I don't get any trouble for that. Alyx is an NPC, but Alyx is the main component, and you're going to see this name come up more and more. It's the central component to our deployment process. Overwatch is a component that takes our servers on and offline, so it controls the traffic to those servers. And then Outpost is the component that lives on the servers themselves and is responsible for updating them. So let me talk you through how this process works. On the left here, you can see that user requests are coming into our load balancer, and we're hosted in EC2, by the way. Those requests then get spread across our web servers, pretty standard. When we go to do a deployment, Alyx reaches out to Overwatch and tells Overwatch, take half of those servers offline. So we divide our servers into 2 sets, 1 and 2, and we'll take set 1 offline. And then next, Alyx is going to reach out to every one of those servers that is no longer receiving traffic and update it. Part 2 then is Alyx is going to reach out again to Overwatch and have those sets flipped, and then it'll update the second set of servers. Now, the nice thing about this is that once set 1 is back online, the code is essentially updated. Set 2, the deployment process is not over, but the code is live. The downside here is that it means that we do have to run at least twice as many servers, so we have enough capacity to do this. So all said and done, it takes about 30 minutes to get through this process. But again, because we can get set 1 live sooner than that, we can actually get it live in 15 minutes, about half of that. Another nice effect of this is that we can do rollbacks by just doing a standard deploy. And this is really important because rollbacks aren't something special. We have tested this process. We know that it works because we use it all the time. And so if we have to roll back code because we had a problem, we just hit the deploy button again on an earlier version of that code. So to sum up to this point, I think, these are mine, not anybody else's, there are 3 keys for deployment: doing it quickly, doing it safely, and doing it during the day. And that last point is pretty critical. I don't know your business, maybe you can't do this, but I don't think you should try to use it as an excuse or a crutch. You should try to deploy when there are people around who are awake and knowledgeable about what's going on. So if there are problems, you can solve it. And because you're doing it during the day and doing it frequently, if you have to deploy it at night because something comes up, you're ready for it and you know that the system will work. So I've brought you up to, and we still use this a little bit today. We haven't gotten rid of it, but we've wanted to improve it. But I want to bring you then to about January of 2012. And we've grown the company a bit at this point, and we had these releases we actually named after video game characters. But in 2012, we had this release we called the DYSON release. And it was because we wanted to clean up our code base. We had a lot of technical debt. We wanted to pay that down. The developers really, really wanted this. It kind of exposed some problems. Now, we were on an agile development release. Our usual typical releases were 3 weeks long, and this one ended up slipping into 5 weeks. On top of that, we have these things called hot fixes, which I've called critical patches here. And I don't have data on this. I have to kind of rely on my memory. But I thought it was about typical for us to have 5 to 7 of these in a regular type of release. With DYSON, we had 14. And this is when we started keeping track. Pretty much as a result of the DYSON release. So we're seeing some problems, and we have to think through what is at fault here. Why did this get so bad compared to our previous releases? And there could be, a lot of explanations for it. But when we analyzed it, we were looking at our company growth, and this just kind of gives you an idea of where we were at in subscribed schools. This is the way that we measured our growth until last year. At this point in the cycle, we're on track to hit 10,000 subscribed schools, so paying schools. And then obviously in the next year, we'd hit almost 15,000. We're growing our team accordingly. So here we're on track to hit 26 people on our product team, so dedicated just to product development. So we decided that the problem here was that our process, we had outgrown it. essentially. And we needed to come up with some way to let us continue to move quickly without experiencing these problems that we had in Dyson. And I want to emphasize that up until this point, the team was monolithic because that's where we started and that's how we had continued. So our process was monolithic. We had one big group that made all of the decisions about what we would change. We had one big group that would actually make those changes. And then we had a small part of that group that would test the changes before they went out into production. Of course, on top of that, because we're deploying all of those changes at once, we were also introducing a pretty good chunk of risk at the same time. So what we decided to do about it was split our monolithic team into smaller teams that we called squads. This is also not original to us. We do a lot of reading and research before we make any decisions like this, and we borrowed this model from Spotify. So if you're familiar with it, these terms will be familiar. So each one of these squads has different disciplines represented. You'll have 1 to 2 developers on it. You'll have usually a project manager, a designer, and a QA member who do our testing and typically are the ones who do the releases. What's important about this is that we gave each one of these squads autonomy to deploy, and they don't have to do it on any schedule. They can do it whenever they feel that the code is ready. That's what I'm going to call the continuous deployment. Now, I'm reluctant to use this term because it'll mean different things to different people. But for us, this means that they can deploy, our individual squads can deploy whenever they are feeling that they are ready to. And there's some major advantages to this. One is you can get really rapid feature releases. We're not dependent on one another or any kind of schedule. So as soon as a feature is ready to go out, we can get it live. It also means that those deploys are smaller and less risky. If somebody pushes a deploy live and something goes wrong, it's pretty obvious where the problem is. It was something in the code that they changed. Now that's true of a big deploy too, except if we're doing that, we're doing a lot of changes at once, you have no idea which one in particular is causing the problem. And is it something that we have to roll back for, try to fix, and then update again, or is it something we can fix live? And for that same reason, then, it's easier to identify problems because these squads are working on one particular thing that's a very small chunk of code that becomes very easy. Now, let's fast forward again here to last fall, autumn of 2013. We've continued to grow. We're at 48 people in our product team, but we still have one GitHub repository for all of our code, and we're now pushing 10 deploys a day, or thereabouts. There may have been a warning sign at this point that I realized when putting this presentation together. We have a deployment queue. So even though we have different teams, different squads, they have to queue up, they have to line up and deploy in order. And maybe looking back, that should have been a warning sign to us. But whatever the cause, we started seeing some cracks in our foundation. These are some of the big ones here. Our repository size in GitHub, so this is compressed, is over 750 megs. On my laptop, when I have it extracted, and I haven't analyzed why this is the case, but it's 6 gigs. The average build time now is over 9 minutes, and our average extraction and warm-up time, so the time that it takes to move the code to the server, extract it, and warm the application up is over 4 minutes. We think that's a problem. So if you do a little bit of math on this thing in a 9-hour day with 30-minute deploys, we're looking at a realistic max of 18 deploys a day. And if we continue growing the way that we're growing, this is going to be a ceiling for us. We're not going to be able to move faster than that. And that's if everything goes right. I'm assuming you know well that not everything goes right. There's a lot of things that can go wrong. We can have operational incidents. EC2 is not perfect. We can have rollback situations. It can take us a while to determine if we even need to roll back. We can have bugs that break scope. And one of my favorite we do things in an interface and service sort of way. We had a situation where service A called into service B or depended on service B depended on service C, and somebody introduced some code where C would then depend on service A again. And that was a lot of fun to figure out what was going on. Then Alyx has some problems, too, that kind of cause some exacerbation of the problem. And that is it can't resume. So if a deploy fails during any part of the process beginning to end, we have to reset state and start that deployment over. So even if we get into set 2 and we're 20 minutes in and the deployment fails, we have to reset and begin again. We also made a kind of a poor decision in that connection between Alyx and Outpost is an HTTP long pole. So it sits there open that entire time waiting for a response. And that's bad, obviously, because if that connection gets broken for whatever reason, then the deployment fails and we have to start again. So just in summary here, and motivating problems into what we did next, was having this one big repository, having a monolithic application and the potential for the downtime of introducing bugs, having what we could consider long build times and long deploy times, and then those process design flaws that I think exacerbated that. So on to part 2 then, and what we did about it. You're going to see a lot of terms here that we borrowed from Norse mythology and maybe the Marvel universe. I'm not going to say it was one way or the other, but we named our project the Multiverse. This is something that we began in December of last year. We wanted to improve this whole process for us and for our customers. You could argue that instead of calling it Multiverse, we probably should have called it YGGDRASIL. This is really intimidating for me anyway to pronounce, so we went with Multiverse instead. You can look that up yourself. The idea is to break it up. So if the problem was that we had a monolithic application similar to having a monolithic team, then the solution must be to break that up into smaller components, and that's what we did. I'm going to use the terms, I'm going to use the term mostly application, but I will probably slip in and use service occasionally, and I'm going to use those interchangeably, so just know that ahead of time. In this context, application and service are going to mean essentially the same thing. Let me give you some numbers up front so you know where we're going with this. Our repository size before at our monolith is 750 megs. A multiverse app now is less than 1 meg. So we've dramatically reduced the size for the squads who are working on their particular app. Our build time has gone, I said earlier we were above 9 minutes. We've actually reduced that just a bit. So our average build time over the last week when I checked on this for Monolith was 8 minutes and 12 seconds. Our multiverse application is now the longest one, takes 34 seconds. Our deployment package size, this is what actually is compressed and moved up to the servers, has gone from 117 megs of a zip file on the monolith down to 20 for the largest app. And the reason that that's 20 megs instead of, you saw 1 meg of source control, we package everything that application needs, so all third-party assemblies go into that same zip file. Our deployment time now has moved from 30 minutes for a full deploy in a monolith to less than 3 minutes for a multiverse app, and this is constant-ish. And then our max deploys per day have gone from 18 on the monolith to 10 times that because we've reduced the amount of time by 10 to 180 per multiverse app. But that's times the number of apps because we can deploy these things in parallel. So this is now a function of how many apps that we introduce into our multiverse. So how do we do it? A lot of research. As I said before, it's our MO that when we don't know what we're doing with a problem, we try to read up a lot on what other people are doing to solve it. This was no exception. We did a lot of reading on Netflix. I have a lot of respect for this company, and they have a lot of similarities to us. They're a video service that also happens to be hosted in EC2, and they have a service-oriented architecture. In fact, if you read Martin Fowler's blog post on microservices, he specifically mentions them. Two things that they don't have in common with us that are relevant. They do their deployments a little bit differently than we do, actually a lot differently. And forgive me if I'm mistaken about this, but my understanding is that when they deploy new software, they actually spin up new instances in EC2 with that software. And we didn't want to do that. They're also based on Java, and we're based on .NET. So there's a little bit of a mismatch there. Let me then quickly define what an app is, at least in this context. And it's going to be guidelines rather than a definition, but I think that it's a subset of features that are closely related to one another. One of our squads is going to develop it, and that squad is going to maintain it over time. But it can be any combination of a backend service and a website section. And that's the reason I use application really rather than service. An application may have components that other services depend on. It may not. It may also contribute to our website. So for instance, Recruit is an application. So if you go to huddle.com/recruit, that monolithic or that multiverse app will serve all of those requests. So essentially what we want to do here is take this and turn it into this. This should look familiar. I just copied and pasted this from our organizational slide. It's the same sort of deal. We might even want to turn it into this, and I think this is ultimately the goal. So I want to talk about this in 3 parts here and introduce you to these concepts in our multiverse. The first part is going to be communication. The second part is commands, and the third part is going to be deployments. Yeah, I tried really hard to come up with another comm thing. It just didn't work. First thing is communication here, and that's Bifrost. This is a component that we wrote ourselves. The big idea behind Bifrost is service location. And it also provides some data transport and load balancing, but service location here is the key thing. Data transport is going to include things like serialization and deserialization and handling the wire protocol. And the load balancing is going to be selecting which server. So we run multiple servers of each multiverse app for redundancy, primarily for redundancy. Service location is closely tied to service discovery, and this is an idea, again, that we took very much from Netflix. For instance, if you have service A and it depends on service B, how does service A talk to service B, or how does it find service B and even know that it exists? And the answer is Eureka. At least that is for us. Eureka is a piece of software from Netflix. This is what it looks like. It's not particularly beautiful, but it's not meant for you. It's meant for computers. The point of Eureka is a service registry. So services that you create register themselves with Eureka, and then other services can look them up depending on what they need. Bifrost, in particular, registers itself with a series of routes. So we take advantage of Netflix's Eureka's metadata component, and we can put in there whatever we want. It's just a set of JSON data. Let me break that out for you a little bit more so it's easier to read. Huddle.routes is the key behind Bifrost. Here you can see all the routes that Recruit has registered, at least a Recruit example application. Anything there that doesn't start with Bifrost is external. That can be accessed from huddle.com/whatever, so /recruit/example. Bifrost components start with Bifrost and are not allowed to be external. And those are the ones that are the service parts of the application. And in case you were curious, we do actually use HTTP for our protocol. We don't necessarily have to do that, but we've chosen to do it because it's easier to debug in this stage of development. So how does that work? To answer that question, A would reach out to Eureka and see this route that says Bifrost/B, and it is a regular expression. So it knows that everything in that namespace must come from B. Now, on the public side, we make heavy use of Nginx. It's our router/reverse proxy, and we're big fans of it. We're not experts in it necessarily, but it's worked for us very well for a lot of years. It does a very similar thing. If you were to go to huddle.com/b/example, Netflix needs to know where it needs to route that. So again, it'll ask Eureka and find a very similar route and then route accordingly. The thing is of course, that Netflix doesn't actually talk directly to Eureka. And so we've written a component that we call Sparkplug, one thing that doesn't actually go with our Norse mythology. By the way, I forgot to mention Bifrost is the Rainbow Bridge. That also comes from there. Okay. So Eureka will, Sparkplug will pull Eureka and constantly and then transform Eureka's routes into Nginx configurations and then just reload Nginx as those things change. All right, on to commands. Our command framework is Mjolnir. This is another one that we wrote ourselves. This name is, again, Norse mythology. This is Thor's hammer. When we originally started our multiverse project, we thought that Mjolnir was going to be multiverse, and so we thought, this is great. We're going to name it after the tool that we're going to use to break apart the application. Now we just think, well, it's a component of it. It's kind of badass, so is his hammer, so we'll go with that. This is based heavily on Netflix HYSTRIX. It is not a port. We've rewritten it, but their ideas have come across into Mjolnir. And so if you're a Java-based application, you should definitely use HYSTRIX if you're interested in this. The concepts I'm going to explain here are pretty much the same. Mjolnir and HYSTRIX provide resilience to failure, and I want to talk about what that means. There are problems when you run distributed systems. Three of the big ones that I can think of are unresponsive servers, service calls that may take too long to respond. So, for instance, code that was deployed and now has bad performance. And then service calls that, for whatever reason, are pretty much consistently returning errors or have a high error rate. And Mjolnir helps you with each one of these things. It's a framework that lives within your service that wraps all of those remote calls. Here are the ways that it responds to it. I'm going to address each one of these. With unresponsive servers, there's timeouts. For service calls that take too long, we're going to talk about thread pools. And finally, with service calls that are returning errors, we're going to talk about circuit breakers. So timeouts, you're probably already familiar with these. Like, what is there really to say about it? The thing is that more than likely you forget about them, because most of us do. And even worse, the framework's default timeouts are actually really long. In .NET, the HTTP client has a default timeout of 100 seconds, and really, when was the last time you waited 100 seconds for anything to happen? It's a minute and a half. In Java, the default is that there isn't one. It just will sit there forever. So Mjolnir, sorry, I forgot. Mjolnir actually will force you to choose timeouts. When you write Mjolnir code, you can either define a default for your application within the code itself, or you can do it on a call. But either way, you have to make a conscious decision on what you're going to do. And what's great about that is you can then optimize what you want those defaults to be over time. So you can keep track of how often your application should respond, say about a second or so, and you can set those timeouts really, really low to like 1 or 1.5 seconds. And then anything longer than that, you can fail. And that's really important, right? Because if that application is going to fail, that call is going to fail anyway, you want to make sure that your users are not going to sit there and wait 1.5 minutes for it just ultimately come back as a fail. And about thread pools. Your system already has this thing, but Mjolnir does something a little bit special. So assume again that this is your service here, and each one of these squares represents another service that it's calling out to, so that the colors here correspond. And this is a normal operation. So you've got a thread here dedicated to calling out to each one of these applications. So what should happen here if somebody, this salmon-colored one, so our salmon service, introduces some code. It's some new database code. They forgot to put an index on the database, and it's now taking maybe 10 seconds for a single call to come through. Each one of these threads is now holding for 10 seconds, and in the meantime, all of your other threads are exiting, leaving up some free space, and so the next calls to that salmon service take up that space, and soon enough, there are no free threads left, and none of your other service calls can get out. Now, nothing is wrong with those, and nothing is really wrong with your application, but it looks like it is, because now everything is hanging. And you can imagine that if there's any service that depends on yours, a similar thing is going to happen, so you've got some cascading failure here. What Mjolnir does is introduces these thread pools, and you can define them however you want to, but you group services together in some kind of logical way that each have constraints around how many threads that they can take up. So if salmon here decides to misbehave again, it will only impact calls to the salmon service. The other three will continue operating as normal. And finally, there's this idea of circuit breakers. With a service, you may have a normal error rate of about 1% here where it's calling out to another service, and that's fine. But what happens if, again, some code gets deployed or maybe a database goes down, and suddenly the error rate jumps up to, say, 75%? We're going to open that circuit similar to a real circuit breaker. If there's too much amps going through, if there's too much current going through, it'll break that circuit. What's cool about this is that this allows us to fail fast back to the client again. In fact, it might actually prevent some problems because if your service appears to be failing, or even if it appears to be correct but most calls are failing, you may actually save some wrong data to your database. It can also reduce load on an already stressed system. And Mueller in particular will automatically heal itself. So it will occasionally let a service call go through and check and see if it responded correctly. If it does, it will go ahead and close that circuit again. This is the first component that we've actually open sourced, so we're trying to give some of this back. We intend to do it with other ones, but feel free to use this and give us feedback. All right, finally, deployments, and this is my baby here. We go back to Alyx. We're on version 3 here. What we've done is we've learned from the first 2 versions that we've done with Alyx. I didn't talk about version 2, but it worked in a very similar fashion to version 1. What we've learned is that we need Alyx to be asynchronous, we need it to be stateless, and we need it to be scalable. Asynchronous insofar as I talked about how we had those HTTP long polls with previous versions of Alyx. We don't want that anymore. We want everything to call into Alyx. Stateless because we learned in version 2, because we built it on Node, and no offense to Node, but it crashed a lot, we assumed that we're going to crash. So we need to make sure that Alyx can recover and the process can continue. And finally, it needs to be scalable, not only to the applications that it's running, but also to our team and the number of people who are using it. I want to give you kind of an inside look at what Alyx looks like. We did a mobile-first development on this, and so that's what it looks like. Alyx is based around the idea of moving branches through a process. So as the team creates a branch, does its development on it, tests it, and eventually deploys it to production, Alyx is going to help them every step of the way by giving them feedback about how far along the process it is, and if it's building or if tests are failing and those sorts of things. I've talked before, I said that Alyx is a central component to the deployment process, the coordinator. These are the services that Alyx depends on or coordinates. Obviously GitHub, I've mentioned that. TeamCity is our build server, it's made by JetBrains. I've talked about EUREKA. You won't see now that Overwatch is here because we've taken it out of the picture. So we're now talking directly to EUREKA. We use Amazon's SNS, that's a simple notification service. It's a pub-sub model, and that allows us to continue being asynchronous. And Alyx continues to talk to Outpost. So here's how the deployment process works for us now. The user triggers a deploy by clicking this button. Again, multiple of these can happen at the same time. Alyx is going to gather some information that it needs. So it needs to know what's the target service, what am I actually deploying? It's going to find out what port it needs, and I'm going to talk more about that in a minute. And then it needs to know where that location, like where the build is actually living. And we push all of our builds up to TeamCity, or up to S3 directly from TeamCity. Finally, it's going to publish, not finally at all, Alyx is going to publish the info into SNS. And that's kind of where Alyx decides to take a back seat now and let the process continue on its own. SNS distributes all the message to all of the servers. And the servers that are listening for it, so in this case, Recruit, they're going to pull that message in and verify that it's actually from Alyx. And then they're going to start the update process. So here's where Outpost comes in. We actually deploy now, instead of 2 different servers, we deploy the same application twice on the same server. We have here Recruit port 8000 and port 8001. The one in blue here is live, taking traffic. The one in gray in this slide is not taking traffic. So Alyx knows that which port or which application is not taking traffic, and it will choose that one to update. As soon as that update is done, Outpost will instruct the new app to register with EUREKA and the old app to deregister. And this process is going to take about 90 seconds as the traffic moves from the old application to the new application. As I pointed out before, Sparkplug is going to update the Nginx configuration as it reads that from Eureka. And then finally, Alyx is sitting there watching Eureka this entire time, and it knows now when the deployment is complete based on that port number and a few other parameters that we put into Eureka. There's one little problem with this. If you're paying attention, you might think, well, it was a little weird that you've got this 90-second gap where traffic could be going to either one, a new app or an old app. And what do you do about that? One particular problem that we've actually seen, and we learned it before we went to Multiverse, is if someone makes a request to a new application and that application has new resources, like new JavaScript or even new versions of their JavaScript, and so their client goes back, their browser goes back and asks for those resources, and they get directed to an old version, they're pulling in the old version of that JavaScript, or it may not even exist, and they get errors. And that's a problem. And we don't want that happening for 90 seconds, definitely. So what we do is we use cookies during the deployment. When the application deploys, it sets a cookie in the browser to the user. And now Nginx will look for that cookie, and if they have it, it will only direct it to new applications. So once you've hit a new endpoint, you can't go back. It won't allow you to go back to the old one. So we basically just bleed off that service during that 90-second window. Once the deployment is complete, we delete the cookie so that it's ready to go for the next deployment. So where we're at now, went a lot longer than I thought it would here. We've gone from no apps in our multiverse up to 7 now, currently. We added 3 in the last month. And here you can see where our deploys are. So in white, you can see our monolith deploys, and in blue, you can see our multiverse deploys, and they're really taking off. Last month in June, we had 60, and our monolith deploys are on their way down as we convert squads over to our new system. So just a little bit about the lessons. I'm going to have to kind of speed through these things, but I want to tell you how we messed up, at least the big ones. We should have considered our product team. We really blew it here. We were so focused on what we wanted to get done and making sure that our users had a good experience, and there's nothing wrong with that, but we didn't take into account how this would impact the rest of our team and how they wanted to get their work done or needed to get their work done. One of the big problems here was we had to install Nginx everywhere, as it turns out. So on a developer's machine, we have to install Nginx. On our test servers, we have to install Nginx. Our designers use Macs. I use a Mac. That's especially fun. We also ended up making our monolith deploys just a little bit worse. Because we have that 90-second window now between switching, there's 4 of those during a monolith deploy, so we've now added 6 minutes to a monolith deploy because it needs to support the new multiverse framework. So that made things a little bit worse for our team. Routing was really, really tough. The question here is, wait, which server is this request going to? It could be that you're developing the application locally, and so you want it to go to your local server. Maybe it doesn't. Maybe you've got another one out in development somewhere on a test server, so we need to be able to figure out where it should go. And failing that, then we can drop back, and we have these things we call our communal Thors or our communal canonical Thors. Thor is the name that we gave to our test environment or test servers. So failing any development branch, we want to fail back to what's actually out in production, but a test version of that. I want to warn you too, be prepared. The first app's going to be really rough. We grabbed our recruit squad and asked them to help us out. It turns out that they did a lot of the work that we as our the tribe, the foundation tribe that was actually working on this project, we couldn't do it by ourselves, and so we relied very heavily on them. They were not only just alpha testers, they were developers in the whole process. So set that expectation up front. And finally, understand your components. The The one that really got us was Netflix. Netflix's Eureka. We're using that one directly. We didn't re-implement it or anything, but we didn't have a full understanding of it. And so there were at least 2 cases where we had issues in production that we blamed Eureka for because we didn't know it, but ultimately ended up being our own fault. Okay, I'm down to 1 minute, but I hope that I piqued your interest. So are there any questions that I can answer for you? Nobody's getting up? All right, great. Feel free to find me afterwards. I just want to point out, we're at about 150 or 160 people. This was our retreat last year. There I am, by the way. But yeah, so thank you very much.